Hi everyone, welcome to our 14th lecture. This lecture is on the conservation of momentum, and it's a combined lecture for both the calc and the non-calc students. It doesn't contain any calculus. Okay, so what we've done in the previous three lectures is we studied conservation of energy, and conservation of energy came out of Newton's laws. And if you recall the roller coaster, which had a curvy path, what I did was I started off by approximating it with straight line segments, and I said, we can make a bunch of wedges which approximate the curvy path of the roller coaster track, and each one of those little straight line segments was like a little wedge, like an inclined plane, and then we could apply Newton's laws the way we did previously, and we would be able to get the acceleration down each one of those inclined planes. And piecing them all together, we got an equation which connected the initial velocity and the final velocity, irrespective of the shape of the path. Okay, and it was that point that it was irrespective of the shape of the path that made it into a conservation law, because conservation laws depend on only your initial condition, your final condition, and it doesn't matter how you get from the initial to the final condition. That logic for the conservation of energy was inside of Newton's laws. Even though Newton himself did not know about the conservation of energy, that conservation law could be teased out. There's another conservation law that can be teased out of Newton's laws, and that's the conservation of momentum. Okay, so the conservation of momentum, it's a different quantity than energy, although the two are sometimes confused. Energy is basically the ability to do work. If something has energy, and say a car is moving and it hits something, well, then it does work on that car because of the energy that it has. Momentum is kind of like that, but momentum is just basically the tendency of something that's moving to want to keep moving, kind of like an inertia, but not quite. Okay, so it's like energy that way, but it's actually a vector, whereas energy is not. So it is different. It is a different quantity. There's a certain momentum in a direction, whereas there's no direction at all associated with energy. Okay, so when we do these problems, we'll talk about in 1D, we'll talk about the momentum to the left or to the right. In 2D, it'll be a momentum of certain magnitude in a certain direction. Okay, if I give you the information in polar coordinates. All right, and where is conservation of momentum useful? It's basically useful in collisions. All right, so whenever you see collisions between multiple objects, momentum is conserved. All right, so I'm not going to prove conservation of momentum rigorously, just like I illustrated the work energy theorem by just showing you an example, the roller coaster, and I said, let's pretend that we would actually do this and see what pops out of it, and we got this work energy theorem. We're going to do something like that here too. So I'm not really going to give you a proof of the conservation of momentum, but I'm going to say consider this very simple collision and look at what kind of a law comes out of it. Okay, and then even though I didn't prove that it applies generally, it does. It does. Okay. So let's start off by considering a 1D collision, and here we go. We have a mass m1, and it's traveling at velocity v1 initially, so this is before the collision. And we have this mass m2, and it's traveling at velocity v2. And you could see that this is a 1D along an air track here, a one-dimensional line here like that. And you're actually going to do this in the lab, which is why I said air track a minute ago. You're actually going to have two gliders, and you're going to take the two gliders, and you're going to cause them collide and then bounce apart. Okay, so m1 traveling at v1 is going to collide with m2 traveling at velocity v2. All right, and that's the initial condition. Now, I don't care about the details in here. And the details could be pretty crazy, which I'll describe some possibilities in a minute. But whatever those details are, after the collision, I find that m1 is traveling with a new velocity, which I'll call v1 primed. Okay, now and m2 is traveling with a velocity which I'll call v2 prime. Now I changed the notation a little bit. Here I'm putting primed for after the collision. We didn't do that before. The reason is I just don't want to overdo the subscripts. Okay, so this would be like v1 initial. Sometimes we put the little not for initial, but then that kind of looks funny because you'd have a v1 0 and a v2 0. So I just decided that v1 by itself like that would be the initial velocity, v2 by itself like that would be the initial velocity, v1 prime primed will be the velocity after the collision. V2 primed will be the velocity after the collision. I said a minute ago that the collision details here could be pretty crazy. I didn't say anything about how these two interact with one another when they come close to one another. They could come together, bounce a few times, because maybe there's some spring in there, and then the spring might break and they might come apart, or they might bounce very hard, and in some of our collisions they'll stick together. In some of our collisions they'll actually break into pieces, and you can even have explosions, so where like one mass will actually break into several masses and so on. So the details here are very general, all right? All I'm telling you right now is that you've got some initial condition and some final condition, and somehow you went from this initial condition to the final condition. All right, so what does this conservation law do? It basically relates all the masses and all the velocities here, okay? And let's see how that happens, all right? So, well, one thing before I do though, I should point out very clearly that that the direction here is important. So take a look at that V1. That V1 is positive, okay, and that V2 is negative. And then after the collision, V1 primed is negative and V2 primed is positive. If you get the signs wrong on these problems, you'll get totally the wrong answer. Okay, so we got to be very careful about that. All right, now we can begin. So let's consider what happens during the collision. And again, I'm not going to worry about the details. So this is where, it's not exactly a proof, but let's just pretend that, there's a certain period of time, which we'll call delta t. You'll see delta t in a minute, during which the two masses are interacting with one another. And during delta t, they exert forces on one another. So the first thing we could say is that when these two masses, m1 and m2, are interacting with one another and they're exerting forces on one another, Newton's third law applies. So what does Newton's third law say? Newton's third law says that if mass 1 exerts a force on m2, that m2 exerts a force back on m1, which is the same magnitude but opposite direction. Okay, so over here I was very careful to define F1, which is the force on m1. So you can see it here. F1 is acting on m1, but it is caused by m2. So m2 is causing F1 on m1. And similarly, F2, it is a force on M2, but caused by M1. Okay, and now because these two forces are caused by a mutual interaction between two masses, Newton's third law kicks in, and we get this equation here. F1 is equal to F2. They're the same in magnitude, so if you put them in absolute value brackets, they would be the same, but their direction is opposite. And in 1D, direction is a sign. So if F2 is in the positive direction, F1 has to be in the negative direction. That's why there's a negative sign right there. Okay, so here's Newton's third law applied to these two forces. All right, now what? Well, now we're going to write these two forces in terms of mass and acceleration by using Newton's second law. So Newton's second law says, look, you can take F1 and you can write that as M1A1. Now, you got to be careful. This should be the net force. Remember, F net is equal to MA. Is this the net force? Well, let's go back to the diagram here and let's take a look. There are other forces acting if we're doing this experiment in the lab, which is on the surface of the Earth, okay? There's the force of gravity down, and then there's a normal force up. But remember, those two forces, the vertical forces, they'll cancel. So gravity down, M1G, will cancel the normal force up, and so they're gone. The only residual force is going to be F1, so the net force is F1. The same thing for F2, okay? So I didn't want to, gloss over that detail. F1 and F2 are the net forces, and the reason they're in the net force is because the other two forces, gravity and the normal force, will cancel, okay? So we've got that F1 is equal to M1A, and similarly F2 is equal to M2A. Okay, great. If we take that and we plug that into our Newton's third law here, okay, for F1 we can put in M1A1, and for F2 we can put in M2A2, and there we go. Okay, now the next thing we're going to do is we're going to recall that acceleration is defined in terms of velocity. Okay, so what's the definition of acceleration? It's the rate at which the velocity changes, which is delta v over delta t. Okay, now for the students that know calculus, you know that that's dv by dt, but it really doesn't matter in this particular problem because this is not exactly a full proof. Let's just think of a as the change in velocity divided by the time. Now, what's that change in velocity? This is the entire acceleration over the time period when the two things interact. So there's a beginning time before which they're not interacting, and then delta t is the time during which they interact, and then after that they don't interact at all. Okay, and so during that time delta t that they're interacting, they're going to undergo a change in velocity, and that change in velocity divided by the time during which that change in velocity occurs is your acceleration. In fact, it's really like an average acceleration, but that's okay. We don't have to, like I said, we don't have to worry about the details here. So for a1, we can replace that as delta v1, that is the change in the velocity for m1, and for a2, we could write delta v2, that's the change in velocity for mass 2. Okay, and so that's what I did next. You can see here, instead of a1, I write delta v1, and what's delta v1? It's the change in velocity for m1 divided by delta t. Okay, and over here I write delta v2 divided by delta t for a2. Notice the delta t's are the same. And that has to be the case because, the time of the interaction for M1 is the same as the time of interaction for M2. It's not like M1 could be interacting with M2 without M2 simultaneously interacting with M1. And so delta T, you could think of it as the time during which that collision occurs. Okay, and so the delta T on both sides are the same. So I can multiply both sides by delta T, and I just get this equation, which is M delta V1 is equal to negative M delta V2. All right. Now, what do we mean by this delta V1? Well, there's a velocity before, which I call V1, and a velocity after, which I'll call V1 primed. Whenever you have a delta, it's the after minus the before. Okay, and so you'll see that for my delta V1, I wrote V1 primed, V1 after the collision minus V1 before the collision. Same thing on the other side. Delta V2 is going to be V2 after the collision minus V2. Okay, and now what I'm going to do is I'm just going to rearrange the terms, and you can see here I've got M1 V1 prime minus M2 V1 minus M2 V2 primed plus M2 V2. Okay, like that on both sides. And what I'm going to do is I'm going to put all the before stuff on the left hand side and all the after stuff on the right hand side. Basically that just means you see that minus M2 V2, I'm going to bring that to the left hand side, and this minus M1 V1, I'm going to bring that to the right hand side. And when you do that, you get this equation, which is M1 V1 prime plus M2 V2 primed is equal to M1 V1 plus M2 V2. Notice that everything on the left hand side of this equation is before, and everything on the right hand side of this equation is after. Not only that, but the structure of the equation is the same. It's M1 V1 plus M2 V2. All right, before. It's also M1 V1 plus M2 V2, but after on the other side. And so what you're seeing here is the conservation law emerging, because there's a quantity we can define, and that quantity is M1 V1 plus M2 V2. We're going to call it P, and we're going to say that P is basically a conserved quantity. P is the momentum. Why it's given the symbol P, I'm not sure, okay? You might think maybe it should be given the symbol capital M, but we've already given M to mass. So to not cause confusion, I guess that's why P has been chosen historically. But everyone calls the total momentum capital P like that, okay? So the total momentum is calculated as M1 V1 plus M2 V2, and it's conserved. Why? Because if you calculate that quantity before the collision and you calculate that quantity after the collision, they're equal by this. And so you could say that momentum after is equal to the momentum before. There you go. There's your conservation law. Not a proof, okay? Meaning, when we say proof, like mathematically, you want to make sure that it covers every possible situation. But I really just looked at this one situation where you had two masses colliding. But there is a proof out there, and it just simply covers all possible collisions, and it's quite powerful. Okay, it's quite useful in many different situations. So this is good enough though for you guys, because the reason to give you this is to give you an intuition into why momentum is conserved. And the answer is it's a combination of Newton's third law and Newton's second law. Newton's third law basically says, look, when these things are colliding, the forces they exert on one another is equal but opposite in direction, okay? And that equal but opposite direction forces are going to cause accelerations on each of the masses, and those accelerations on each of the masses are related to one another because of Newton's third law, okay? And you can get those acceleration by Newton's second law, okay? Reduce the forces to the acceleration using Newton's second law, and the accelerations are just changes in velocities, and out comes the conservation of momentum, okay? So this momentum is kind of like, like how much is the system kind of moving in some direction, irrespective of how the little pieces are moving, like the totality of the system. The totality of the system has some total momentum. And during the collision, when these masses collide with one another, they're not going to change that overall motion of all the pieces moving together. It's something like that, okay? So that's enough for the theory. Let's jump in and start to do problems, and I think you'll start to see how this works. Okay, so this is you're gonna do this in the lab, and in the lab you'll see these collisions, and they'll be quite intuitive, and you'll be able to calculate the same kinds of problems that I'm going to be doing right now. Okay, so a 300-gram glider is traveling to the right with an initial velocity of 2 centimeters per second. It collides with a 150-gram glider at rest. Okay, so what you should picture is you have a 150-gram glider and you've got a 300-gram glider, and the two collide with one another. Okay, the 150 is at rest and the 300 is moving at 2 centimeters per second. Okay, now I've got a series of questions about the different possible after situations, but this is your before situation. Okay, so A, it is found that after the collision, the 150-gram glider is traveling to the right with a velocity of 3 centimeters per second. How fast and in what direction is the 300-gram glider moving? Okay, so if we find that the 150-gram glider is traveling at 3 centimeters per second, how fast must the 300-gram glider be traveling? All right, so let's see if we can solve that one. All right, and actually there's a part B, but I'll come back to that. All right, in part B I have them sticking together, and I actually even added a part C after this. But let's look at part A first. So in these problems, you should probably draw an initial and final condition, or initial and final situation. Here's our initial situation, and so here's our one-dimensional track, and we have the 300-gram mass here. Okay, and it's traveling with so m1 is 300 grams, and it's traveling with a velocity v1 of 2 centimeters per second. And here's the 150-gram glider. Okay, and it has no velocity initially. All right, then the final situation is they collide. Here's the 300-gram. We don't know how fast it's going. We don't even know if it's going to the right or to the left. Okay, so don't make assumptions. That'll come out. It'll come out in the signs. Okay, but the 150-gram is traveling at 3 centimeters per second. Okay, now I could have emphasized here, I could have put a plus in front of the 2 centimeter and a plus in front of the 3 centimeters to say it's traveling in the plus direction, which is to the right, but I didn't do that. Okay, but for instance, if you had a negative 2 centimeters per second here, then that would be traveling to the left. We'll see that in a bit, but I just wanted to make sure we were very clear about that. Now, I have a little bit of an aside here about solving these problems. You'll notice that the numbers I gave you are in units of grams and centimeters per second. In fact, those are the units in the lab. You can convert to MKS, but if you're very careful and you work all masses in grams and all velocities in centimeters per second, you'll be fine. And the reason is, let's go back to the formula here that we derived. You see, if all of these masses are grams, 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 then the grams cancel out across, okay? And if all the velocities are centimeters per second, they're like that, they'll also cancel out, okay? Now that doesn't always happen. All right, it doesn't happen, especially when you have some kind of squared quantity, like in energy, you have a v squared. So you really can't do that there, okay? Because you won't get an answer in joules. But here, if you're careful, and you say, you know what, I'm going to do all my masses in grams, then that's fine. If you want to convert, you can, but let me just show you how silly it is. Here you'd have 300, but you're going to have 300 divided by 1,000, then 150 divided by 1,000, 300 divided by 1,000, 150 divided by 1,000. It's like each of the m's have a divide by 1,000, and if you're dividing all the m's by 1,000, that just cancels out across the entire equation anyhow. So it just saves you an extra step. All right. So let's be careful. I'll sort of point out what equations you can get away with that. Get away with not converting to MKS. This is one of them. I'll point that out. All right. All right, so that's my little aside there. Now, what do we do? Well, let's find the total initial momentum. Okay, so here's P, and this problem only has two masses. We can have many masses, all right? So there are only two masses, and so we have M1V1 plus M2V2, okay? And just substitute in the numbers. M1 is 300, all right? V1 is plus 2 centimeters per second. M2 is 150. V2 is 0, and that just turns out to be 600 grams centimeters per second. There is no MKS shorthand for momentum, okay, like there is for energy. There are joules, all right, but there's no such thing for momentum, okay. So there it is in non-MKS units, but that's still good enough, all right. And now let's calculate the total momentum after. The total momentum after P primed. P primed we know is 600. So it's not like, I shouldn't have said it that way. I shouldn't have said calculate the total momentum after. Use the formula for the total momentum after and recognize that the total momentum after is the same as the total momentum before. So we have the 600 grams centimeters per second. There it is right there. So I just took P primed and I replaced 600 there. And for M1, that's still 300, the 300 gram glider. V1 prime, we don't know. That's what I'm asking for. If you go back to the question, I say, what's the velocity of the 300 gram glider after the collision? If M1 is the 300 gram glider, its velocity is V1. After the collision, V1 primed, okay? And the 150 gram glider is moving to the right at 3 centimeters per second, so that's why I put plus 3 in there. Okay, and then the rest is just some simple algebra. We got 600 is equal to the 300 V1 prime plus 450, and that turns out to be V1 primed is plus 0.5 centimeters per second. Okay, so it turns out that that 300 gram glider actually has enough momentum that it not only gives the 150 a kick, but it continues in the same direction. Remember, it started off at 2 centimeters per second before the collision and dropped down to half a centimeter per second after the collision, but still in the same direction, still to the right, okay? And the 500 grams started at 0 and it sped up to 3 centimeters per second. There are two pieces to momentum. There's the mass and the velocity. So you can have like a big mass traveling at a big speed, and that's going to be a very big momentum because both m and v are big. Okay, if you have a small mass, with a big velocity, that could be a moderate-sized momentum. Even though the mass is small, the velocity is big, and it compensates for it. Or you can have a big mass with a small velocity. Okay, if both mass and velocity are small, then of course it's the total momentum is extra small. So the reason I'm saying that is because this should sort of fit your intuition. You see, yeah, M1 is still moving in the same direction, but you might expect that because M1 is much bigger. Well, not much bigger, it's twice as big as M2. And so, yeah, it's going to transfer some of its momentum to M2, but it's still going to have some momentum left over, okay, in the same direction. All right, so there's part A. For part B, I won't scroll back up. What I said was, let's imagine that these two gliders, they come together, but they stick. They stick. And so this interaction is an interaction where, I guess that delta t could be like infinite. So, they stick together. All right. And so the before picture looks the same, so I didn't redraw it. Okay. The before picture is still this. I still have the 300 gram traveling at 2 centimeters per second to the right and the 150 at 0 velocity, okay? But the after picture now looks like this. The after picture of the two masses, M1 and M2, stuck together, and both of their velocities, V1 primed to V2 primed, prime meaning after the collision, they're equal to one another and unknown. That's what we're solving for, okay? So we know that P primed is the same as P, the total momentum before and the total momentum after are the same. That's a 600 grams centimeters per second, so there it is. But for M1 V1 primed plus M2 V2 primed, I said, you know what, let's just call V1 primed and V2 primed, let's just give it one name, V primed. Because that V primed is the velocity for the combined M1 and M2. Both of them are going to be traveling at the same speed because they're stuck together. Okay, that's what we mean by sticking together. Okay, that they're going to be, moving together, which means that they'll both have the same velocity. So to not confuse the velocities here, we're going to remove the subscripts because we don't want to suggest that V1 primed is different than V2 prime. We'll call both of them just V prime. So if you replace V1 prime by V prime and V2 prime by V prime, you can factor it out and you just get M1 plus M2 times v primed. Okay, and that kind of makes sense because how do you calculate momentum? It's mass times velocity. If you've got many pieces, you do m1 v1 plus m2 v2 plus m3 v3 plus m4 v4. We'll see that as we go on. Every single mass in your system will have an mv contributing. But here, if their masses are stuck together, there's just one mass, and its total mass is m1 plus m2, and its total velocity is just v primed. So there you go. This is again m, but m now is the combined mass times v. All right, so let's continue. We have 600 gram centimeters per second. That's the total momentum. Is got to equal 300 plus 150. The m1 is 300, m2 is 150 times v primed. Okay, and it's very simple to solve for v primed. You just get that v primed is going to equal plus 1.33 centimeters per second. Does that make sense? Okay, before we go on to my part C, does that make sense? Well, before we had the 150 standing still and the 300 coming in at 2 centimeters per second. They're going to stick. When they stick and they collide, you expect that the resulting velocity is going to be less than 2 centimeters per second. It doesn't make sense that they come together, they collide, and then they actually go faster. That doesn't make any sense. So you don't expect this number to be bigger than 2. We don't expect it to be 0. That doesn't make sense that they just come together and stop, okay, because there is some momentum to the right that is in the positive direction. We don't expect the momentum to change and start going into the negative direction. That makes even less sense, okay? And so, yeah, 1.33 makes sense, okay? In the positive direction towards the right, okay? So the two masses, they stick together, and they will travel with 1.33 centimeters per second, all right? So details of the collision in both of these are very different. In fact, I didn't even tell you the details of the collision in part A. You don't know what happens in there. All you know is that after that collision occurs, there might be some bouncing back and forth if there are springs in there. And who knows, again, what the details are. All I tell you is that after the collision's done with, you found that the 150 was traveling at a certain speed. How fast was the 300? And you were able to answer that. Here, you don't know the details of the collision. Like if there was some kind of like a sticky spring in there, okay, they might come together, stick, and then bounce back and forth a little bit. In which case, the two velocities would not be the same. But that might dampen out, and then eventually, it dampens out. When it does, they'll be traveling at 1.33 centimeters per second. Okay, great. Here's part C. In part C, the before picture is still the same. Okay, in part C, I have my 300 gram mass breaking apart, exploding, breaking apart into a 200 gram piece. So I called this one M1 primed. Okay, and that's 200 grams, and I called this other piece M3 primed. Okay, and that's 100 grams here. And so the 300 gram actually breaks into a 200 plus a 100 gram. Okay, and the 200 gram piece, after the explosion, after the 300 breaks apart, the 200 gram is moving to the left at 1 centimeter per second. The 100 gram chunk is just sitting there at 0 velocity, and I want to know how fast that 150 gram piece is moving. Okay, and so let's answer that. All right. So just to be very clear, this M1 primed and M3 primed, okay, those two together, that is the 300. After the collision, it broke apart. Okay, so you know that during collisions, like heaven forbid you should ever be in a car collision, but you know that when cars collide, pieces will go flying off in all different directions. Conservation of momentum still applies. It still applies to all the pieces that are flying apart. Okay, and so what we have here is the 300 being broken up into a 200 and a 100. The 200 moves to the left at 1 centimeter per second. The 100 doesn't move at all. It just kind of sits there after the collision, and I want to know how fast that 200 is moving. Okay, so there are 3 contributions now to the momentum, and so P primed is going to equal M1 primed, which is a fragment. M1 primed is a fragment of the original M1, V1 primed. So M1 primed times V1 primed plus M3 primed. Again, M3 primed is a fragment of M1, the original M1, multiplied by V3 primed plus M2. M2 didn't break apart, so that's still the 150, multiplied by V2 primed. So after the collision. Okay, so P primed, the momentum after the collision is the same as the momentum before. That's still 600. Notice that didn't change all the way through the problem. No matter what my after situation is, I had 3 possible after situations, but doesn't matter which one it is, it's still 600 because 600 was the initial momentum. Okay, and now we just substitute in for m1 prime 200 because that's the 200 gram fragment, and it's traveling to the left at 1 centimeter per second, so that's why that's a -1 in there. M3 primed, that's 100 grams. V3 primed is 0 because the 100 gram fragment just sits there, okay, after the collision. And M2 is the 150, and we don't know how big V2 primed is. Okay, we don't know. Why? Because that's what we're solving for. We want to know how fast the 150 is moving. Okay, so the rest of it is just simple algebra. We get 600 is equal to -200 plus 150 times V2. V2 turns out to be positive 5.33 centimeters per second. Okay, at this point you might wonder, that's a pretty big number there. Is that right? And the answer is yes. Okay, and that's going to be my next point. So this is actually leading into my next problem. Yeah, this is going to be moving faster than 2 centimeters per second to the right. And you're going, geez, what's happening here? What happened was when these two pieces came apart here, there was a tiny little explosion. There might have been some energy added to the system. Okay, and so you can have situations where your energy before and after are not the same, and yet the momentum is still conserved. All right, now that's a bit confusing. You might go, well, isn't energy always conserved? No, remember there might be friction, and so energy can be lost to heat. And so in those cases, when energy is lost to heat, the energy after the collision is less, but the momentum is still conserved. All right, you can have energy conserved and momentum conserved, but you can also be in the situation where the opposite of energy going to heat, you can have heat going to energy. And you go, well, what does that mean? Actually, that's really like what happens in a chemical reaction. In a chemical reaction, you can actually get energy released from the microscopic level, which is the chemical bonds, and then that can become macroscopic energy, which you could see as the energy of things flying apart. Okay, and I'm going to show you that in a minute, so I'm going to make this very clear. But I want to get this idea of energy clearer now, because next, like I said, next semester we'll talk about heat in detail. But when energy is lost to heat, when you've got energy, a lot of energy before, and then it dissipates away after, so you've got less energy afterwards. You say the energy was lost to heat. That's energy going from macroscopics, where you can see it, into the microscopics, into like the details of the atoms and molecules. Okay, but the opposite can also happen. You can have energy in the microscopics, in the atoms and molecules, in the bonds between the atoms and molecules, and that energy can be released and become macroscopic, and that's what an explosion is. Okay, so there are 3 possible collisions that can occur. Okay, and these are called inelastic, elastic, and superelastic collision. Momentum is always conserved. Okay, so momentum is conserved, but energy doesn't have to be. And again, energy isn't conserved if energy is lost due to the frictional forces, or energy is added to the system because of, like I described, chemical energy simply produces some kind of macroscopic energy. Okay, and so we have 3 possibilities. We can have collisions where the energy is conserved, so both the momentum is conserved and the energy is conserved. Okay, and in those cases, elastic collisions, the energy is conserved. Okay? We call those elastic collisions. So in elastic collisions, the energy is conserved. All right. Inelastic collisions, remember, momentum is always conserved. So in an inelastic collision, the momentum is conserved, but the energy is lost to heat. Okay, so we actually have a decrease in energy during inelastic collisions. And then the third type of collision, as you might guess, are called superelastic collision. And this is where the energy increases, and the energy increases because of some explosion. Okay, somehow energy was added to the system during the collision. All right, and so there are 3 possibilities there. Let me show you how you can have momentum always being conserved, but energy sometimes conserved, sometimes lost, and sometimes gained during a collision. All right, so I have one before picture, and here's my before picture. This is really simple to do the math, so we could just even do it in our heads. Okay, so before, the total momentum in this system is 0. Why? Let's take a look here. We have a 1 kilogram mass traveling at 1 meter per second to the right, and we have a 1 kilogram mass traveling at 1 meter per second to the left. Okay, very symmetrical situation. And so if we say, well, what's the total momentum? m1v1 plus m2v2. What's m1v1? Well, that's 1 times 1. Great. So that the momentum for this mass right here, where my cursor is 1 kilogram meter per second. Conversely, the momentum for this other mass here is negative 1 kilogram meter per second. 1 kilogram meter per second plus negative 1 kilogram meter per second is 0. Okay, so the before picture here is a system with 0 momentum. The momentum of each of the masses exactly cancels the other. All right, but what's the total energy of this system? All right, so when we did conservation of energy, we were usually just thinking about one roller coaster car going downhill. Okay, but here we have two objects, and they both have kinetic energy, because this mass has kinetic energy and this other mass has kinetic energy. Both masses are moving, so both of them have kinetic energy. There's no potential energy here, okay? They're not going uphill or downhill. Everything's on a flat surface, and there's no springs or anything like that. And so if you calculate the total energy, you say, well, what's the total energy of this first one? Well, the total energy is 1/2 mv squared. So for the first one, you can calculate the energy as 1/2 m1v1 squared, okay? And you can calculate the energy for the other one as 1/2 m1v2 squared. Well, the m's are all 1 and the v's are all 1, so all you're going to get is a half plus a half, okay? And that turns out to be an energy of 1 joule. All right, so that's how I got the numbers. Let me just summarize. Total momentum for the system before, 0. Total energy of the system before, 1 joule. Okay, so we have a system with no momentum, no total momentum, and energy 1 joule. All right, here are 3 possible after scenarios, okay? So they're all different, okay? So here, after, both masses collide and they stick together, and they're moving with 0 velocity. Okay, so both masses were coming in like this, and they collide, and they just stop, all right? So what's the total momentum after? 0, okay? It has to be, because the total momentum before was 0, the total momentum after has to be 0. So P prime is 0. What's the energy now? The energy now is, well, neither of the masses are moving. So if you do 1/2 mv squared for each of the masses, you're going to get 0. 0 plus 0 is 0 joules. So take a look at what happened. The before picture, 0 momentum before, 0 momentum after. Good, because momentum must be conserved. Was energy conserved? No. We had 1 joule before, 0 joules after. Okay? So the energy went from 1 joule down to 0 joule. Where did that energy go? Heat. Heat. Okay, in whatever the details were that stuck these things together, you could measure actually the increase in heat. Again, not to repeat myself too much, but next semester we'll actually be able to calculate the heat. We'll actually be able to calculate the change in temperature during this collision, but not right now, okay? Right now, all we need to know is that we were at 1 joule and we're down to 0 joules. All right, so that's one possible after. Here's a different after, okay? Here's a different after. So like don't picture this one anymore. Okay, so just picture this as a possible different after. It's like a movie with 3 possible finales. Okay, here we have a 1 kilogram mass. Remember, it was moving to the right, but after the collision, it's moving to the left. Okay, and here's the 1 kilogram mass. It was originally moving to the left, but now it's moving to the right. During the collision, the velocities flip, so it was traveling 1 meter per second to the right. Now it's traveling 1 meter per second to the left, and vice versa for the other one. Okay, so if you calculate the total momentum, this one has a total momentum of negative 1 kilogram meter per second. This one has a momentum of 1 kilogram meter per second. So negative 1 plus 1, 0. Okay, good, because the total momentum before was 0. The total momentum after is 0. Momentum is conserved. What about the energy? Well, again, the energy for each of these is 1/2 mv squared. 1/2 1 times 1 squared. The negative 1, when you square negative 1 for v squared, the negative goes away. So this one has a half joule. The other one has a half joule. A half plus a half is 1 joule. Okay, so what was the initial energy? 1 joule. After this collision, still 1 joule. So the momentum was conserved, as it must be, and the energy was conserved. And so this is an elastic collision. Okay, great. So there's another possibility. The third one is I have the two bouncing off of one another, but now when they bounce off, they're traveling in the opposite direction faster, actually 3 times faster than they came together. They were coming together at 1 meter per second, but now they're bouncing apart at 3 meters per second. Is the total momentum here is still 0. Well, yeah, because if you do the momentum for this mass right here where my cursor is, it's -3 now. It's going to be -3 kilogram meters per second. So this one has -3 kilogram meters per second momentum. This one has +3 kilogram meters per second. -3 plus +3 is 0. Again, the momentum after the collision is 0, as it must be, because momentum is always conserved. All right. What about the energy? Well, now we do 1/2 m1v1 squared plus 1/2 m2v2 squared. The masses stayed the same as 1, but the velocities, they're 3. And if you work this out, it turns out to be 9 joules. So if this is your after situation, you started at 1 joule, but then after the collision, you're at 9 joules. Momentum is still conserved, but the energy increased. Why did that energy increase? Well, you have to have something like the opposite of your inelastic collision. In your inelastic collision, you had energy and it went into the heat and it went into the microscopics between these two things as they stuck together. Here, it's got to be the opposite. Here, maybe there was like a little bit of nitroglycerin in there, just like a tiny crystal of nitroglycerin. And so the energy was in the microscopics, and after the collision, that energy was released and went into the macroscopic motion of the objects, okay? And so that's why the energy might increase. But nonetheless, the momentum is conserved, okay? So, yeah, you have 3 different collisions. Momentum is always conserved. But if the energy stays the same, we call it elastic. If the energy decreases, it's inelastic. And if the energy increases, then it's superelastic, okay? So there you go. Let's do a problem here to illustrate this. So I have a 3, so my before situation is I have a 1 kilogram mass moving to the right at 3 meters per second, and I have a 3 kilogram mass moving to the left at 1 meter per second. Okay, so there's my before situation. There's a collision, and I tell you that this collision, the energy is conserved. In other words, this is an elastic collision. And now I want to find the velocity of both the 1 kilogram and the 3 kilogram after the collision. Okay, notice you have 2 unknowns here. In the previous problem, when there was only conservation of momentum involved, you had only 1 unknown and you solved for it. But here there's 2 unknowns, and you go, well, how am I going to be able to solve for 2 unknowns? And the answer is you're going to have 2 equations in 2 unknowns. One equation for the conservation of momentum, and because this is an elastic collision, another equation for the conservation of energy. All right, so let's do that. So here I say both P and E are conserved. Okay, let's look at P first. Okay, so with P, how do you calculate that? It's m1v1 plus m2v2. All right, so I did this and I just substituted in the numbers. 1 traveling at 3 to the right, 3 traveling at 1 to the left, and that gives me a total momentum of 0 kilogram meters per second. All right, next. Well, there's the before, here's the after, P primed, and that's m1v1 prime plus m2v2 primed. P primed must be the same as P because momentum is conserved, so we'll put a 0 there. The masses didn't change, nothing broke apart or stuck together or anything like that. And so m1 is still 1, m2 is still 3, and we get this equation here, which I call equation number 1, and it just says that v1 primed plus 3v2 primed is 0, okay? So it's 1 equation and 2 unknowns, and you're going to need another equation in the same unknowns in order to solve it, all right? So there's as far as we can get making use of conservation of momentum. What about conservation of energy? Well, conservation of energy, we have this equation for the conservation of energy before. If we plug in all the numbers, so m1 is 1, v1 is 3, m2 is 3, and v2 is -1. The -1 squared will go away, the negative will go away. And so this turns out to be a total of 6 joules, okay? It's an elastic collision, and so energy is conserved. And so over here, when we do it again, E primed, that's the energy after the collision, it's the same formula, m1/2 m1v1 but primed squared plus 1/2 m2v2 primed squared, like that. And we substitute in all the numbers. We don't know v1 primed and we don't know v2 primed. And so we get 6 is equal to half times 1 v1 prime squared plus a half 3 times v2 prime squared. Okay, multiply this throughout by 2 so that everything works out nicely into nice numbers, and you get that 12 is equal to v1 prime squared plus 3 v2 prime squared. Okay, so this I'll call equation number 2, and I just rewrote equation number 1 here like that. Okay, now I'll tell you, these problems can get very hard to solve from this point on. It's pretty easy to get to equations 1 and 2, but from this point on it can be really hard, and I made this problem easy. I made this problem easy because the total momentum was 0. If the total momentum is not 0, then you're going to be squaring a whole bunch of um, um, polynomials. Okay, um, so let's take a look here how we might solve this. And the first thing you might do is go, you know what, because you've got two equations and two unknowns, so you got to substitute one into the other. The easiest thing to do is to start with equation 1 because that doesn't have any squares in it, and isolate either v1 primed or v2 primed. It's easiest to isolate v1 primed, obviously, and then substitute for v1 primed into there and to solve for v2 primed. So that's what we'll do. Using equation 1, let's eliminate v1. And I should have put a prime there, v1 primed first. So we have v1 primed is equal to negative 3 v2 prime. That's just this equation bringing the 3 v2 prime to the other side. Okay. And now substitute for v1 primed into equation 2. So equation 2 says 12. There's the 12 equals. But for v1 primed, let's put in negative 3 v2 primed squared plus 3 v2 primed squared like that. And that just reduces to 12 is equal to 9 v2 prime squared plus 3 v2 prime squared like that. And then just solving for v2 primed, I get that v2 primed is 12 divided by 12, or 1. And then you take the square root of that, and be careful, the square root, when you take the square root of 1, it's actually going to give you negative 1 or positive 1. Okay, so you go, well, do I really need both signs? Yeah, you do, because you can't, you don't know whether an object's going to be moving to the right or to the left. Okay, so you have to consider both possibilities. So I mean, I kind of skipped a little step in there, but it was a very simple step. It's basically that v2 primed squared is equal to 1. 12 divided by 12 is 1. Okay, now if you have something like, let's change the variable name. If you have x squared is equal to 1, you say, well, what possible things could I put in for x squared? X squared is equal to 1. Well, you could put 1 because 1 squared is equal to 1, but guess what? Negative 1 squared is also equal to 1. And so there's always two solutions. Whenever you have a square, there's two solutions, and you might have to consider which one you want. In this case, if you go back to the diagram here, it's pretty clear that v2 primed has to be positive, okay? But you know, like we might have solved for v1 primed, and then we would have gotten two solutions too. And here we want v1 primed to be negative. So don't just jump to the conclusion that you want the positive solution. You may want the positive solution, you may want the negative. And you go, well, how will I know? And the answer is look at the diagram and decide which one you want. So you want the positive solution for v2 primed. So down here, after we got that v2 primed was either positive 1 meter per second or negative 1 meter per second, I say from the diagram it's clear that v2 prime must be positive, and so we want the positive one. Okay, and then once you've got v2 primed, you can use equation 1 again. That's this equation right here. So you've got v1 primed, solve for v2 primed. Okay, and sorry, the other way around. You've got v2 primed, solve for v1 primed. Okay, and when you substitute in there, you'll just get that v1 primed is negative 3 meters per second. Okay, so what does the after picture look like? The 1 kilogram piece is moving to the left at 3 meters per second, and the 3 kilogram piece is moving to the right at 1 meter per second. If you look at this problem, you look at the before and after. Okay, so here's the before. The before is 3 meter, the 1 kilogram moving at 3 meters, and the 3 kilogram moving at 1 meter. Okay, and you say, well, what does it look like after? And after, you have the 1 kilogram still moving at 3 meters per second, but in the opposite direction. And the 3 kilogram moving at 1 meter per second, but in the opposite direction. Kind of makes sense, okay? That symmetry worked out here. It worked out symmetrically like that because the total momentum was 0. If I'd made this a harder problem and I'd made the total momentum equal to 1 or something like that, you would see that this kind of symmetry, you know, where, you know, it was traveling 3 meters one way and then traveling the 3 meters the other way, that would have been broken, okay? And it would also have been a lot harder problem because when you went to equation number 1 here, when you isolate v1 prime, you wouldn't just have in terms of v2 prime, you'd actually have a term in there, and then when you put it in the square, you'd have to use like FOIL, okay? And so when you expand that, and so it would have been a more difficult problem, okay? But still doable, but nonetheless, I just wanted to show you how that worked out. So this is an example of making use of the fact that a collision was elastic to determine both V1 and V2 after the collision. All right, so you could actually have two unknowns. All right, that's enough for 1D. Let's move on to 2D. So in 2D, and this is where momentum becomes much harder than energy. In 2D, momentum is a vector, and so you have to treat these like vectors. And that means you have to bring in all that machinery of polar to Cartesian conversion. Okay, now what does the conservation of momentum look like in 2D? Well, without proving it, basically you have a statement like P primed is equal to P. All right, the momentum after is equal to the momentum before, but you have to put little vector hats on it because there are two components there. Okay, so it's the total momentum before as a vector must equal the total momentum after as a vector. Okay, that means it has both a magnitude and a direction. Now, how will we do that? So my little symbol here means implies. So the fact that the total momentum before and after as vectors is conserved, that implies that if you look at the x component will be conserved, and the y component independently will be conserved. Okay, so the way we will solve these problems we will break up all the velocities in the x and y components, and with the x components of the velocity, we'll calculate the x component of the momentum, and with the y component of the velocity, we'll calculate the y component of the momentum, and then we'll insist that the x component before and after the collision must be equal, and independently of that, we'll insist that the y component of the momentum before and after must be the same. Okay, so that's how we'll solve the problems. All right, let's do a problem, and let's see how this works. So in this diagram, I wouldn't say I was lazy, but I combined both the before and after picture together. Okay, and not to be lazy, but just to show you, what it looks like. Because if I'd done the two diagrams separately, I don't think it would have been as clear. So the before picture, as I have M1 and M2 here. Okay, notice I say yes, this is before. Right there and there, okay? So M1 is traveling along the x-axis towards the origin, and M2 is traveling along the x-axis towards the origin. That's the before situation. What happens is they collide at the origin and they stick together, okay? So what does my after situation look like? My after situation looks like M1 and M2 are stuck together, and they're traveling at some velocity there, like that, okay? So there's the after. Now I give you some numbers. M1 is 3 kilograms, okay, and it's traveling at 5 meters per second along the plus x direction, okay. M2 is 4 kilograms and it's traveling at 4 meters per second along the plus y direction, okay. And of course, the combined mass when they stick together, M1 plus M2, that must be 7 kilograms, okay. And finally, there's some velocity here, v1 primed, as a vector, because it has both an x and y component, and I want you to find the final velocity, v1 primed, as a vector, okay? And actually, this is a slightly ambiguous way of asking it. I'm going to ask for that answer in polar coordinates, all right? So let's do the problem. Well, first, what equations are we going to use? So we're going to use the same equation that we used above, but we're going to have one version of it for the x component and one version of it for the y component. Above we had m1v1 plus m2v2 is equal to m1v1 prime plus m2v2 primed, but now we have m1v1x plus m2v2x. What's that x mean? Just the x component, and that's got to equal m1v1x primed, so x component of mass number 1 after the collision, plus m2v2 primed. That's the velocity of mass 2, x component only after the collision, okay? So there's the x component. What would the y component look like? The equation for the y component? The same, just replace your x's with your y's, okay? So how do you get this v1x and this v1y and so on? Well, I give you those velocities. All right, implicitly you got those velocities from the diagram, okay? And so this velocity here, that 5 meters per second, it has an x and y component. The x component of this velocity is v1x. The y component of this velocity is v1y. Over here, this is mass 2, so here you have a velocity v2x for its x component and v2y for its y component, okay? And then finally here, these two are combined together. All right, and so here we're going to have a Vx primed and a Vy primed. Now I know in these equations I wrote them as M1 plus M2, but remember the two masses are the same, so are not, sorry, the two masses combine. And so v1x primed and v2x primed are really just vx prime, because the 1 and 2 are stuck together. And we saw that in our one-dimensional problem where we had a collision where things stuck together. You'll have the same situation here. Okay, so now it's a matter of identifying these components. In this particular problem, identifying the components are easy, because my next problem will be more difficult. But here it's easy, because you see that 5 meters per second is purely in the x direction. So this 5 meters per second has an x component and no y component. Over here, this 4 meters per second has a y component but no x component. Okay? Whereas this final v of the combined mass has both an x and a y. All right? And so let's do that. So for m1 equals 3 kilograms, v1x, that 5 meters per second is purely in the x direction, so v1x is 5 meters per second. Okay, v1y is 0. All right, so just take a look here. All right, which way is the velocity going? It's going in the positive x direction, and the so it's 5 meters per second in the positive x direction, and there's no y component. There's no vertical component to that velocity at all. Okay, now at this point I got to point out something which is a common mistake that students might make. Take a look at where m1 is. M1 is on the x-axis, but on the negative side of the x-axis. Okay, but that's the position. We don't want to put a negative for the velocity in there. Yeah, the position is somewhere in the negative x-axis, somewhere along the negative x-axis. But what direction is the velocity heading in? The velocity is heading in the positive x direction. Same thing for m2 here. M2 is in the negative y, along the negative y-axis here, like that. But its velocity is actually in the positive y direction. So students will sometimes make that mistake. Don't make that mistake. We're not looking at where it is, that's like your position. We're looking at what direction it's moving in, the velocity. The velocity is moving in the positive x direction. The velocity here is moving in the positive y direction. So it's positive 5 meters per second and positive 4 meters per second for the x and y components respectively. All right, so here we had the 3 kilogram. v1x was positive 5 meters per second, and there was no y component for v1. For m2, the 4 kilogram mass, there is no x component for that one because it's traveling straight along the y. Okay, so there's no x component there. But the y component is 4 meters per second, and it's in the positive y direction. All right, so I hope that's clear. Now what? Well, we can calculate the total momentum before. So the total momentum before, basically that's the left-hand side of these equations. All right, the left-hand side of these equations. Px is going to be m1 v1x plus m2 v2x, and just plugging in the numbers, m1 is 3, and its x component is 5, m2 is 4, but it's got no x component, and so you get a total momentum x component 15 kilogram meters per second. The y component, same thing, but now with y's. m1 v1y, v1y is 0, okay, because the velocity of mass number 1 has no y component. It only has an x. Has no has no y component. The y component of mass 2, that's the 4. Okay, and so just substituting these numbers from here into there, we get 3 times 0 plus 4 times 4, which is 16 kilogram meters per second. Okay, so there you go. There's the total momentum in the x direction and the total momentum in the y direction before the collision. After the collision, we have that px primed, that's going to be m1 v1x primed, okay, plus m2 v2x primed. But we saw when we have collisions where things stick together that basically the two masses just factor out, so we get m1 plus m2 multiplied by whatever the velocity is of the combined masses, and we will call that vx primed. Okay, and we know that that px prime must be the same as px because the x component of the momentum is conserved. And so here for px prime, you can put in 15. The two combined masses, m1 plus m2, is 7. Okay, so a 3 kilogram mass sticks with a 4 for a total of 7. And so we can solve for vx primed. And vx primed is the velocity of the combined masses after the collision, x component only. Okay, and that turns out to be 2.14 meters per second. All right, so there we go. We're done with the x component. With the y component, we have py primed. Okay, so py prime must be the same as py. Again, that's the conservation of momentum, and that we found to be 16. All right, On the right-hand side, the two masses will combine and they'll have a common velocity, but we're only looking at the y component, so it's Vy primed. The two combined masses, a total of 7, 3 plus 4 is 7, and multiplied by Vy primed like that. And now, just working it out, it turns out that Vy primed is 2.29 meters per second. Great, we now have the velocity of the combined masses after the collision, okay? We have the combined velocity there. We have it though as a Cartesian vector. We have its x component and we have the y component of that vector. All right. Now, like I said at the beginning, I didn't say whether to answer in Cartesian or polar. On a test, I'd be very clear about this, but we're doing this together. So let me say, what, I want this in Cartesian. So no, sorry, I want it in polar, but you have it in Cartesian. And so let's convert it. Okay, so if you have Vx primed is 2.14 and Vy primed is 2.29, in polar, we want the magnitude and the direction. To get the magnitude, you use Pythagorean theorem. So v prime, that's the magnitude of the velocity after. That's just how fast it's going irrespective of the direction. How do you get that? Square root of vx prime squared plus vy prime squared. Okay, and so you square the x component, square the y component, add them together, take the square root, and that turns out to be 3.13 meters per second. Okay, so we know that this thing is traveling at 3.13 meters per second. What about the direction? Okay, well, the direction, you use the inverse tangent, and I think it's pretty clear that the direction is in towards the first quadrant. So let me be very clear here. Let's go back to the diagram. I know the mass is in the first quadrant, but that's not what we're looking at. We're looking at the direction of that velocity. The direction of that velocity is also into the first quadrant. So it's traveling into the first quadrant. Okay? So, like you could have you could have the mass here, but you could be traveling this way. See how my cursor, I'm moving it up like that? That would be traveling into the second quadrant, okay? And in that situation, you'd have to use a slightly different formula. You'd have to add that 180 in there, but not in this case, okay? So, whoops. All right, so you use the angle is the inverse tangent of the y component divided by the x component, and that turns out to be 47 degrees, okay? And so if you take a look at that on a diagram, you'd have the combined mass, the combined 7 kilogram mass, moving at 3.13 meters per second at 47 degrees, like that, okay? So there you go. There's the answer in polar. Do the numbers make sense? Okay. Well, let's take a look here again, just to remind you of those numbers. Whoops. We had 3 kilograms moving at 5 meters per second. We had 4 kilograms moving at 4 meters per second. We expect this to be somewhere in the vicinity between like 5 and 4, okay? Or not between 5 and 4, but around 5 and 4, okay? And it's actually slightly less because it's actually 3.13 because now, all of that is in a combined mass of 7, okay? So it turns out to be traveling at 3.13 meters per second. So everything's kind of in the right ballpark. And also you kind of expect that, if, one mass is traveling in the positive x direction and another one's traveling in the positive y direction, the two combined have to be somewhere between the x and the y direction. And it is. It's actually at 47 degrees to the positive x direction into the first quadrant. All right, so there's our first problem. That problem was made easy because, back here, because I put the velocity v1 purely along the x direction. I put the velocity v2 purely along the y direction, okay? What if they had been at some angle? So that's our next problem. Okay, and so here I have two masses. Again, 3 kilograms, 5 meters per second, 4 kilograms, 4 meters per second, but look at the angles. And this one's no longer traveling along x, and that's no longer along y. This one's traveling in at this 45-degree angle like that, and this one's traveling in at 30 degrees like that, okay? And they collide and they stick, okay? So I didn't show the after picture here at all right? They collide and they stick. In fact, in this one, you might be hard-pressed. Your intuition might be hard-pressed to decide whether the combined mass is going to be traveling into the fourth quadrant or into the first quadrant, okay? Let's not worry about that. Even if your intuition can't tell you which way it's going to be going, that'll come out afterwards when we solve the problem, okay? But you see, let's let's take a look at what we have to do now to get the total momentum before, okay? So this 3 kilogram mass, it is in quadrant 2. That's its position is in quadrant 2. But its velocity is actually heading towards what? Quadrant 4. And that's very confusing to students. Okay, you go, well, what do you mean? Like, how should I do this? So what you should do is don't look at where it is. Look at which way it's going. And the way to do that is, you see how I have that little cross there? Put a little temporary uh, X and Y axis right on the mass, and then ask yourself which direction is the velocity vector pointing in, and you can see that it's pointing into quadrant 4. Okay, never mind that its position is in quadrant 2. The position here, see, this is like y-axis this way, negative x-axis that way, so this is quadrant 2 there. The position is in quadrant 2, but the velocity is quadrant 4. Now, just to show that very clearly, let me blow up this picture right here. And if I do that, here it is. Okay, here's the 3 kilogram mass. Here's my temporary x and y axis on it. And there is my 5 meters per second. Notice that my 5 meters per second is actually heading into quadrant 4. Okay, and also this angle, this 45-degree angle, be very careful. Okay, we want the angle that it makes with the positive x-axis. The positive x-axis, when it's attached to the 3 kilogram mass, is right there. Okay, and so the angle we want is over there is 45. Now if that's 45, then that's also 45 by I forget the name of the theorem, parallel lines theorem I think it's called. But you know, I think it's pretty clear that this angle in here has to be 45, but we're measuring it in the clockwise direction, so it's actually negative 45. Okay, and so the angle that the 5 meter per second velocity vector makes with the x-axis is negative 45 degrees. Okay, let me say that again. The angle between the x-axis and the velocity vector is negative 45 degrees. Okay, we have a magnitude 5 meters per second. We have an angle with the x-axis of negative 45 degrees. Now we can use the formulas for getting the x and y component. Okay, the x component is v1x 5 cosine negative 45. Okay, which is the same as 5 cosine 315. Okay, so another way, if you don't like negative angles, is you could start here and go all the way around until you get to there. If we did that, if we're here at the positive x-axis, by the time we get to the positive y-axis, 90 degrees, then 180, then 270, then 270 plus another 45 gets you to 315. Okay, but you could do this on your calculator. If you calculate negative cosine of negative 45 and cosine of 315, you get the same answer. Okay, so I just did that, you know, because some people go, I don't like that negative 45. Fine, you can start with the positive x-axis, go counterclockwise though, and if you go counterclockwise, by the time you get to the vector, you will have traveled 315 degrees. You would have turned 315 degrees. Or conversely, you could start at the positive x-axis and turn clockwise. That's in the negative direction, 45 degrees. Okay, and so that gives us an x component of 3.54 meters per second. Okay, do the same thing for y, but with sine, 5 sine negative 45 degrees, and that gives you negative 3.54 meters per second. Notice that the x component is positive, the y component is negative, quadrant 4. Okay, now what? Well, you know, I went through a lot of detail for that 3 kilogram. Same thing for the 4 kilogram. So for the 4 kilogram, I know it's in quadrant 3. Sorry, it's in quadrant 3. But just take a look at the velocity vector. The velocity vector is heading into quadrant 1. And again, you can put a little temporary xy axis right on that 4 kilogram mass there like that. Let's blow that up over here. Okay, so here's the 4 kilogram mass. And here I said, look, the angle in there is 30 degrees. So if this angle in there is 30 degrees, well, then that angle in there has to be 30 degrees like that. Okay, and so in my expanded picture here, you'll see that the angle in there is 30 degrees. Okay, so 4 meters per second at positive 30 degrees to the plus x-axis. So 4 cosine 30 degrees, 3.46 meters per second. There's your x component. And your y component for sine 30 degrees, which is 2 meters per second. Okay, so what I did was, all that work was just to get this velocity here, this 5 meters per second, and break it into x and y component, and here this 4 meters per second, and break it into an x and y component. Okay, so once I did that, I can now go ahead and calculate my total momentum before, because my total momentum before has an x component, that's this line here, and a y component, which is the line underneath it. The x component is m1v1x plus m2v2x. Okay, substitute in the numbers. M1 is 3, V1x, if you scroll above here, V1x was 3.54. And so for V1x down here, I put in 3.54. And then M2 was 4, and V2x, okay, that was that 3.46. There's the 3.46. Working that all out on my calculator, I got 24.46, okay? And this is kilogram meters per second, but I dropped the units here, okay? Py, same thing, all right? But now for V1y, I put in negative 3.54. Again, that's from above. And for V2y, I put in 2. That's the 2 we found here, okay? So we found the x and y components so that we could substitute into this equation. And that gave me a total momentum, y component of my momentum of negative 2.62 kilogram meters per second. Okay, great. So we've got the total momentum before the collision. What's the total momentum after? The same, but that's got to equal now the combined mass m1 m1 plus m2 multiplied by v, x and y component. Okay, so here we go. Let's start off with the x component of the momentum after. All right, so the primes there mean after the collision. So, and the subscript x means just the x component. The x component of the momentum after the collision has to be the same as the x component of the momentum before the collision. So you see that 24.6 right there? That's that px prime must also be 24.6, okay? The two masses combined, so m1 plus m2, 3 plus 4, there's 7. And there's only one velocity after, and that's the combined velocity v prime, but we're looking at only the x component, so vx primed, okay? And you take a look at that line there and you go, oh, I can solve for vx prime. That's right, vx primed is 3.49 meters per second. There we go. We've got the x component of the velocity of the combined masses after the collision, 3.49 meters per second. Do the same thing for y. For y, we have py primed, total momentum, y component after, is got to equal the combined masses multiplied by their combined velocity, y component only, okay? And for py primed, must equal py, conservation of momentum. So for py primed here, put in that negative 2.62, negative 2.62. That's got to equal the combined mass, 3 plus 4, multiplied by the y component of the velocity after, and this gives us a vy primed of negative 0.374 meters per second. Okay, great. This answers the question in Cartesian. The x component of the velocity after, 3.49 meters per second. The y component of the velocity after, negative 3.47. Okay, 3.74, sorry. Okay, convert this to polar because it's a little easier to think about it in polar. To get the magnitude, just use Pythagorean theorem. So that's the 3.49 squared plus the 0.374 squared. Take the square root of that, gives you 3.51 meters per second. Okay, and for the angle, we have to use the inverse tangent formula. But look at this. The x component is positive, the y component is negative. So this actually turns out to be into quadrant 4. This is in quadrant 4. You may not have expected that because your intuition might not have told you whether it would be heading into quadrant 1 or quadrant 4. You kind of know that it has to be quadrant 1 or quadrant 4. It can't kind of turn the other way, okay? But you weren't sure whether it would be going above the plus x-axis or below the plus x-axis. Well, the fact that vy primed is negative tells you that it's actually going into quadrant 4, okay? And so because we're in quadrant 4, when we do the inverse tangent, we should add 360, okay? So I did that, and it's the inverse tangent of the y over the x component, okay? And I calculated, and I get this negative 6.2 plus 360. Now that we've done enough of these problems, we've thought about polar a lot. We don't really have to add in that 360. You can, but you know what? You could just think of this as negative 6.12 degrees in the clockwise direction, so slightly below the x-axis, okay? So these two masses were coming in like that, okay? They were coming in, and they collided at the origin. And the 7 kilogram mass travels at 3.51 meters per second, but at this negative 6 degrees to the plus x-axis, okay? All right, part B. A problem like this, a 2D problem, where I want you to calculate two unknowns. telling you that it's an elastic collision is very difficult. Okay, the math would drive you crazy. Okay, you can do it. It's just algebra. There isn't any like calculus involved in that, but it would be a lot of algebra. Okay, but I can ask you to determine whether whether this collision is elastic, superelastic, and inelastic. And the way you would do that is you just calculate the total energy before, and you calculate the total energy after, and you know the numbers, so you can calculate the total energy before and the total energy after, and you compare. Did the energy stay the same? Then it's elastic. Did the energy increase? Then it's superelastic. Did the energy decrease? Then it's inelastic. Okay, so this is actually, part B is actually pretty easy. All right, so let's do that. We calculate the total energy before. All right, and the total energy before is 1/2 m1 v1 squared plus 1/2 m2 v2 squared. This is not a vector, so you don't have to worry about the x1, v1x and v1y or anything like that. No, just v1. Just v1. In other words, the velocity before you decompose it into x and y components. And v1, the 3 kilogram mass, was traveling at 5 meters per second. And the 4 kilogram mass was traveling at 4 meters per second. Plug in the numbers and work it through. It turns out that your energy before was 69.5 joules. Okay, what about the energy after? Well, there's only one mass after. Okay, so the energy after is 1/2 total m, which is m1 plus m2, multiplied by their combined velocity squared. Okay, the total mass is 7, 3 plus 4. Okay, the velocity after, this is just the magnitude of the velocity. We found that to be 3.51 meters per second. Squared that, and turns out to be 43.1 joules. Okay, now what do? Just compare the 69.5 to the 43.1. This was the before, that's the after. Did the energy increase or decrease? If you compare one to the other, the energy decreased, and if the energy decreased, then the collision is inelastic. Okay, well, I'm going to tell you a little, I don't know if it's a secret, but a little heuristic, and that is that whenever masses stick together, it's always inelastic. Okay, you can't have a situation where, no matter what the details of the collision are, no matter whether it's even 1 or 2D, if you have two masses and they stick together, the energy will always be less afterwards. Okay, again, it's one of those things you can easily prove, but I'm not going to prove it for you. And so, so any collision where masses stick together, they're inelastic, and you can determine that right away. Okay, so there you go. There's an example of a 2D conservation of momentum problem, and we can still ask whether it's elastic or inelastic. We're not going to make use of the energy, but we can afterwards analyze it and say, did we lose energy, did we gain energy? And by analyzing that way, we can at least label the collision as either inelastic, elastic, or superelastic. All right, so another topic, and then we're done. We're going to move on to extended objects. Okay, so up to this point, we were really only worried about masses acting like point masses. Okay, so you remember when we did masses sliding down inclined planes? Remember how we put all the forces to the middle? We kind of put a little dot in the middle of our box, and we attached all the forces to the middle. And the reason is that because the object wasn't rotating or doing anything like that, we weren't really worried about the extended nature of the object. All we were worried about was, just the acceleration of the total object itself. Okay, and so that wasn't, something that we didn't want to complicate our physics by bringing that in too soon. We're going to be moving into the physics, the motion of extended objects. Okay, and before we do that, we should look at this thing called the center of mass. Now, the center of mass actually comes out of the conservation of momentum. I'm not going to show you how that happens here mathematically, but if you've got a bunch of masses and they're like colliding with one another, and again, their collisions could be very crazy. So like they might have forces between them, like a gravitational force where they bounce and then they get attracted to one another, or it could be an electrical force. The things are bouncing but they get attracted to one another, and so on. And so you have this complicated system of many, many little masses all interacting with one another in complex ways. Okay, and you might think, well, the boundaries to that system are kind of fuzzy, but maybe not, because if I take this remote here, I can think of this remote as being made up of a bunch of little molecules, and each one of those molecules is a little mv, a little mass traveling at a certain velocity, and they're all colliding with one another doing crazy things, and yet this entire object has a kind of identity to it, a center to it, which if I threw it, that center would follow a parabolic path. So what I'm trying to say is that objects which are extended can be thought of as being made up of as many point little masses, many masses. Each mass is like just a little point, okay? And these point masses are all bouncing and colliding with one another, so they're conserving momentum, okay? And in the middle of this mass of this mess of masses, there's one special point, and that special point is the point that if you threw the object, that's the point that, say, would follow that parabolic path. That's the point where all the forces are acting when we were doing the forces moving down the inclined plane and so on. So I'm not going to prove this because it's actually not that hard, but it wouldn't help your intuition anymore. There's just this special point, and that special point is called the center of mass, okay? And the center of mass is special because if we have an extended object, and now an extended object is like my remote here, it's not just a point mass. It's not a mass where we don't care about like its spatial dimensions. This point mass has some extension in space. It has some width, height, and depth to it. Okay, so this extended object has a motion if I were to throw it. Now we're not in the classroom, and I always love doing this in the classroom where I throw things in the classroom. I ask students to watch very carefully what happens. So if I usually throw an eraser, but if I were to throw this remote, okay, what would you see? Well, you would see that the remote follows the parabolic path, which we got out of 2D kinematics. But you would notice very carefully that it's the center of this remote that's following the parabolic path. The remote itself might be rotating as I throw it. So if I throw it in kind of like at an angle like this, or kind of giving it a spin, the middle follows the parabolic path, and the object itself spins around. So let me see if I can demonstrate. It would spin like this as it follows the parabolic path. Okay, something like that. Okay, so I think you can imagine this. If not, if you have an eraser at home, carefully throw it, and you'll notice that it spins, but it also follows the parabolic path. And you go, well, what's following the parabolic path? The middle of it, and the middle of it is this thing called the center of mass. Okay. And that center of mass can be identified by factoring out the time out of these molecules as they bounce back and forth, and you get this equation, which I'm going to give you in a second, and it's the equation for the center of mass. So just to summarize, the motion of an extended object, okay, so now you know what an extended object is. It's an object which has some mass, but the mass fills some volume of space, okay? Okay, so this extended object, the motion of that can be analyzed as the motion of the center of mass, and that's basically all the physics that we've done up till now. I didn't tell you that we were talking about only the center of mass when we did like the free body diagrams for those blocks. I said just put all the forces as if they were acting at the center. But now I can say put all the forces as if they were acting at the center of mass, okay? So it's basically the motion of an extended object can be analyzed as the motion of the center of mass plus the motion of the object about the center of mass. This about the center of mass, that's the topic of rotational motion, which is the last topic in the course, okay? So this center of mass is important. How do we find it? Okay, so here's how you find it. In 1D, it's kind of the weighted average of the masses, okay? So this x means the position of the center of mass in 1D, and you calculate it by doing, if you've got a bunch of little masses, remember the extended object, how should you be thinking about it? It's a bunch of little masses. A bunch of little masses. You could go right down to the microscopic level, okay? In which case you'd have like 10 to the 23 molecules in here, okay? And each one of those would be like a little mass at some position x1. So m1 x1 plus m2 x2 plus m3 x3 plus m4 x4 and so on, okay? You can kind of see the momentum part of this. Instead of x's, we had v's, but we factored out that velocity. That's the part of the math that I'm not showing you, okay? So we have m1 x1 plus m2 x2 plus m3 x2, all divided by the total mass of the system, which is just m1 plus m2 plus m3 and so on, okay? So this is kind of like a weighted average. Well, it's not kind of, it is a weighted average, okay? It's a weighted average, all right? And so here I explain the formula where m1, m2, m3 are all the tiny masses that make up the extended object, okay? And x1, x2, x3 are the positions of m1, m2, m3 respectively. Okay, and obviously if you take m1 plus m2 plus m3 and you add up all the little masses, what do you get? Well, you get the total mass of the extended object, which we could call capital M. Okay, so there you go. There's the equation for the center of mass. It kind of makes sense. Like I said, it's a weighted average. What I mean by weighted average is the bigger M1 is, the more it pulls the center of mass towards it. Okay, so if M1 were really big and all these other masses were really small, then the center of mass would be closer to M1 than it would be to the other ones. But conversely, if M3 is very big and M1 and M2 and all the others are small, then the center of mass would be pulled more towards M3 than the other one. So the weighted part of it means, how much influence do each of these masses have? The bigger the mass, the more it tends to pull the center of mass towards it. Okay. All right. So not a difficult equation. So let's just do a problem here. And so here we go. I say find the center of mass for the following. So this is one of my crazy dumbbells, and we have a 1 kilogram mass attached to a 3 kilogram mass attached to a 2 kilogram mass attached to a 1 kilogram mass. Now the bars that attach them, don't worry about the masses of those things. We'll say that they're negligibly small, and it's all along a straight line here like that. Okay, and the distance between M1 and M2 is 1 meter. The distance between M2 and M3 is 1 meter, and the distance between M3 and M4 is 2 meters. And I say, where's the center of mass? By the way, the center of mass is also where the thing would balance. Okay, and we'll see that at the beginning of next semester, actually. But if I put my finger under my remote right here, okay, and I let go, well, it's pretty obvious I didn't balance it very well. But if I put my finger somewhere in the middle here like that, and you got the idea. There we go. Not doing such a good job, but you got the idea. If I put my finger right below the center of mass, it would balance it. Okay. So where is that center of mass here? You might guess it's somewhere in there. I don't know, but let's do it. Let's do it precisely. Those x's are actually vectors. Okay. And in 1D, that means you have to worry about whether it's a positive or negative x. Okay. So we'll set up a coordinate system, and here we go. This is our ruler. Okay, so the problem is up to here, and this is part of my solution here. I'm going to put the ruler. That's the first step. And you might as well put one of the masses at x equals 0. Okay, so my M1, that's going to be right at the 0 of my ruler. Well, if that's the case, then M2 is at 1 meter, M3 is at 2 meters, and M4 is at 4 meters. Okay, and so I have that here. X1 is 0, X2 is 1 meter, X3 is 2 meters. See that? It's at the 2 meter mark, and X4 is at the 4 meter mark. And now we just plug into the equation. It's that simple. Okay, so you got m1x1 plus m2x2 plus m3x3 plus m4x4. So the masses were 1, 3, 2, and 1, and the positions were 0. There's 0 there. There's the 1 meter. There's 2 meters, and there's 4 meters. Okay, and then you divide by the total mass, which is 1 plus 3 plus 2 plus 1. Okay, and when you work that all out, that works out to 11 divided by 7, or 1.57 meters. Okay, so that's where the center of mass of this object is. And where would that be here? It'd be at 1.7, like maybe 1.6, right about there, right about there. So, if you really had this dumbbell, and it's kind of heavy, right? Because, it's made up of 3, 4, 5, 6, 7 kilograms. Okay, 7 kilograms, like 14 pounds. But still, if you had this thing and, you put your hand, like you grabbed it right there, that point right there, you could balance it there. It wouldn't want to flip one way or the other way. It wouldn't want to flop either way. Okay, if you grabbed it over here, I think you could imagine that this side here would be much heavier than that side, and so it'd be hard to hang on to it there, or hard to hang on to it over there. But if you grab it in the middle, and precisely at 1.57 meters from this x equals 0 point like that, then you'd be at the center of mass. You could easily grab it. Also, if you were to throw this thing into the air and it would spin around that point there like that. No matter how complex that spinning is, the point about which it would spin would be right through there. Okay, so there you go. There's the center of mass. Now, what if you have 2D? Okay, in 2D, it's the same as the 1D. All right, it's the same as the 1D, but you've got two formulas. You've got one formula for the x component and one formula for the y component, and they look identical to one another. Just take the formula for the x component above and replace all the x's for y, and you've got the y component. Okay, I didn't rewrite the formulas. I'm just going to do that in the context of a problem. All right, so here's my problem. All right, and I'm sorry that the diagram is not the best, but we have an x-axis here, we have a y-axis here, and we have 5 masses. Here's mass number 1, here's mass number 2, it's on the x-axis, here's mass number 3, it's on the y-axis, and here's mass 4, and here's mass 5, somewhere in the plane. Okay, and over here I give you the numbers. Okay, so you don't have to read them off the graph, but that 5 kilogram mass, where is it? It's right at the origin. So x1 is 0, the x component of mass number 1 is 0, and the y component of mass number 1 is 0. So the 5 kilogram mass is at the origin. The 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 3 kilogram mass, that's M2 here. Okay, it's on the x-axis, so its x component is 2 meters and its y component is 0. The 3 kilogram mass, sorry, M3, the 2 kilogram mass here, which is M3, M3 is equal to 2 kilograms. It's at an x component of 0, okay, an x component of 0, but a y component of 2, okay? And then M4, which is 1 kilogram, well, it's somewhere out here. It's at 3, 2, okay? So it's at x equals 3, y is equal to 2 meters. And the 5 kilogram mass I put at 4 meters, 4 meters. Okay, so x5 is 4 meters and y5 is 4 meters. Okay, now what? Well, we calculate the x and y component of the center of mass. So here's the formula. This is exactly the formula above, all right? Only now expanded for 5 masses rather than just, whatever I had above 3 or 4. Okay, so we have m1x1 plus m2x2 plus m3x3 plus m4x4 plus m5x5. Okay, and it's easy enough to plug in the numbers. You plug in the masses in here for the m's, and you plug in only the x components. Okay, so ignore the y components. They don't come in yet. For the x component of the center of mass, just use the x components here. Okay, and you can see them in here. 0, 2, 0, 3, and 4. 0, 2, 0, 3, and 4. Okay, so we work that out, and we get that the x component of the center of mass is 1.8125 meters. Okay, so that's just the x component. What does the y component formula look like? Take this whole formula, and wherever you see x's, replace it with y's. So here we go. Here's the y component formula. It's m1y1 plus m2y2 plus m3y3 plus m4y4 plus m5y5, all divided by the total mass. Okay, and now in these numbers here, of course, you still use the masses, ignore the x's, and you use the y's. Okay, you use the y components there, and plugging those numbers in, it's pretty trivial. Plugging those numbers in, it turns out that the y component is 1.625 meters. And so the center of mass of this object is at x is equal to 1.8125 meters, and y is 1.625 meters. Okay, if you were to locate that in my diagram, I have a tiny little x right there, which is roughly, at about 1.8 and 1.6, right? Roughly right there, okay? Now you'll notice that the center of mass isn't at any one of these masses. Just like above in my previous problem, the center of mass wasn't at any one of the masses. It was somewhere in the middle of the masses. And here it's in the middle of the mass. And you might say, well, how would these masses even stick together? I don't know. I mean, they're in a plane, so maybe there's like some thin plexiglass that's holding them in place or something like that. And if you were to try to balance this thing, you would have to put your finger right there on this plane, and then it would balance. It would balance, okay? Right there. All right. So there it is. Now, before I finish, the human body also has a center of mass, and I can't stand and show you this, but the human body is flexible, in case you haven't noticed. And the center of mass, if you're kind of standing straight up and like rigid, the center of mass is somewhere around, your belly button or something, maybe a little below your belly button. Okay, that's where your center of mass is. But what if you made kind of a curve? Like, what if you tried to turn your body into a donut? Okay, what you can do, you just lean over and kind of make a round. You know where your center of mass would be? It'd be out in front of you. Okay, and the reason is because you're kind of making a donut. In fact, rather than picturing the human body, how about just picture a donut? Where's the center of mass of a donut? It's right in the middle. Okay, so the donut, you can't put your finger at any point on the donut and expect it to balance. You'd have to put your finger right in the middle of the donut, in the hole, and then it would balance. You go, but there's no donut there. I know. Well, you know what? Put a little toothpick in there or something like that, and then you could balance it on that toothpick. Okay, if the toothpick went right across where the center of mass is. Okay, so something like that. So the center of mass is a little bit of a, yeah, everything spins around that point, but it's kind of tricky. Okay, it's kind of tricky. All right, and I gave the example of the human body, and we'll consider deformable extended bodies, extended objects later. But right now, when I said extended object here, one word I should have probably put in front of it is rigid. Okay, because what we're really assuming is, yeah, we've got these masses, but these masses are kind of stuck at particular positions. Okay, and because if they start to move around, then your center of mass is going to move around to. Okay, just a kind of a subtlety, but I wanted to mention that, especially for the students that are going to head into kinesiology, because in kinesiology you're going to talk about the center of mass of the human body, and the center of mass of the human body, because the human body is not rigid, it's a flexible object. It is an extended object. Extended just means the mass is extended over some volume of space. It is an extended object, but it's an extended object which is flexible, and as you keep changing the shape of the human body, you're going to move your center of mass around. Okay, there you go. There's the end of our lecture on conservation of momentum and related topic, center of mass. Thank you for listening.